All right, so now I am going to solve some more examples. We are still in section 7. So the first argument says P implies R, Q implies R, P or Q, therefore R. So let's prove this. Well, if you look at those statements, by using any of those premises, for example, I cannot use Q implies R and R modus tollens, for example, or modus ponens. So therefore, I'm not going to be able to prove this conclusion. So I have to use indirect derivation. So the conclusion is R, all right? This is what I would like to get. So let's number them. So 1, 2, 3. So I'm going to start with the assumption, suppose the conclusion is not true. So therefore not R. All right, so this is assumption for indirect derivation. Okay, so what else? Well, now I can use modus tollens because Q implies R and not R implies not Q. So this is modus tollens thanks to arguments 2 and 4. Very good. Well, what else? Once I use not Q, I can use, oh, by the way, by using not R and P implies R, I can also conclude not P is true as well. So modus tollens again, thanks to argument 1 and 4. I don't know if I'm going to use it, but let's see. So what I have, line 7, this time I can use not Q and P or Q. So thanks to modus tollens MTP, modus tollens ponens, well, the names are pretty complicated to me. So I have to have P is true, right? P or Q is true, not Q is true, so therefore P is true. Very well. So this is MTP, thanks to argument 3 and 5. So what do I have? I have P and not P. They can't be both true. So therefore I got the contradiction. So I conclude my sub-proof because I already proved that. Well, remember I did use all the inference rules correctly. So the contradiction does not occur because of any of those premises or any of those assumptions except that one, because everything here is true under the assumption that not R is true. So if something is wrong here, well then that must be wrong. So not R is false, meaning R must be true. So this is indirect derivation thanks to argument from 4 to 7. I'm sorry. Okay, so that was the conclusion I was hoping to get, and therefore this is a valid argument and this is the proof of it. Now I'm going to jump to the second example. In the second example, I have two premises. P or Q implies R, not R, therefore not P. Okay, so once again, not P is my conclusion that I would like to reach. So I'm going to call them number 1, 2. So once again, I'm going to do indirect proof, and I'm going to assume that my conclusion is not true. So therefore not P is true. So assumption for indirect derivation. Well, as usual, this is double negation. All right, so therefore P must be true. So double negation thanks to argument in line 3. So once I have P, well, I can add, so that I can make P or Q statement, I can add Q into this. P or Q is still going to be true because this is just addition rule. Addition rule, I'm adding to sentence in line 4. So once I have P or Q implies R and P or Q by modus ponens, I must have R true. So this is modus ponens between argument 1 and 5. So what do I have? I have P or Q, R. Okay, there you go. I got the contradiction. Let me just repeat line 2, all right, not R. I am repeating line 2. I can repeat as many lines as I can, as I want. So I have a contradiction, so that means that's the end of the proof, the subproof. That means there's something wrong. Everything is correct except this assumption, therefore. So not P is false, which means not P must be true. All right? So therefore, this is indirect derivation thanks to argument 3 to 7. And so that's the conclusion I was hoping to get. And this is, so this is a valid argument. All right? And this is how we prove it. And the third example is a theorem. It doesn't have any premise. It's just a statement. Not P and not P. All right? So, well, I mean, if you just think about it, it's intuitively true, right? It's kind of obvious. P, whether it's true or false, P and not P, right, has to be false. All right, so if P is true, not P is false, so P and not P is false. If P is false, not P is true, therefore this is false. So therefore, regardless of the truth value of P, this statement must be false, and hence negation of must be true. So therefore, this is a true statement. All right, so therefore, this is the, well, this is a valid argument with no premise. But the thing is, well, sometimes it's harder to prove obvious things. So how do we prove a theorem like this? All right, we're going to start assuming the opposite. So suppose my conclusion, which is this statement, is not true. All right, meaning not P and not P is true. This is assumption for indirect derivation. All right, and then this is double negation, P and not P, double negation of the line, of the statement in line 1. So this is and, so basically by simplification, I can say P is true, simplification of the statement in line 2, and then not P is also true. This is again simplification of line 2. Well, I can't have both P and not P, so this is a contradiction. Right? So contradiction cannot occur because of this statement, because this statement is simplification of the second one. All right? If this is true, this must be true. This is the simplification of the second one. If this is true, this must be true. All right? So there's nothing wrong in these deductions. And this statement is true if this statement is true. So therefore, everything in this box is true under the assumption that this statement is true. But there's something wrong. So that means this statement cannot be true. So it is false. If it is false, then that means so the negation of my statement is false. So therefore, ignore the negation. My statement must be correct. So 5, not P and not P is correct. This is indirect derivation between line 1 to 4. So this is how I prove this theorem. All right? I hope this is clear.